Hello, everyone, and welcome to Neurocracy. Today, we're joined by Dr. Joshua Gold, a professor of neuroscience at the University of Pennsylvania and co-director of their Computational Neuroscience Initiative. Dr. Gold's research focuses on how the brain processes uncertain information and uses it to make choices, ranging from simple perceptual decisions to complex adaptive behavior. Dr. Gold, thank you so much for joining me today.
Thank you so much for having me.
So my first question for you is what got you interested in decision making as a research question, and why is that such a hard question to answer in neuroscience?
Yeah, it's a great question. I mean, it's really the obvious thing. We make decisions all the time. There are lots of big decisions we make, life choices, where we're going to go to school, who we're going to spend time with, but also little decisions that we make all the time. Are we going to step out onto the curve because we think it's safe? Or, what route do we want to take home? To me, it gives a window into a lot of the really interesting things that our brain does. How do we take the collection of all the things we're seeing and hearing and feeling and combine it with the things that we've learned and know and use that to govern our choice of actions? And one of the really appealing thing to me, in addition to being sort of big questions, is that there are versions of it that we can study in the lab, which makes it a practical tool for sort of understanding higher brain function.
Yeah. So speaking of the lab, what approaches do you use to study decision making? Because I feel like it's kind of hard to study it, right? Like it doesn't, there's no like obvious way that you can kind of, gain insight into that
Yeah,
process. Yeah.
yeah. I mean, the first step is defining decisions that we care about, right? And sort of an operational level, how can we build a task that has people or animals as part of our and other people's experiments make decisions in a way that we can control the inputs and measure the outputs. And so my work started by building on a really exceptional sort of history of work that's been done in so-called perceptual decision making, which is the subset of decisions that is based really specifically on how do we take noisy information from the sensory world and use that to make judgments about what we perceive. And the specific version, and I may refer to it off and on in our talk today, sort of jargony, we call the random dots task. It's a visual task where we control on a computer monitor, typically what someone is looking at. And it's a bunch of little dots moving around. You can think of it as almost like a swarm of bees. And we're asking the very simple question, as a whole, is the swarm moving to the right or to the left? And the nice thing about it is we can control what percentage of the swarm is moving in one direction. We can make it sort of arbitrarily hard or easy. And it gives us this sort of leverage into an actual operational task that we can then start to study.
Yeah. So, when I was looking at your research, these two terms, inference and learning, came up a lot. So I was curious, could you explain a little bit about why these two terms are so important, for understanding decision making?
Yeah, so inference really is sort of just the catch-all term for this sort of basic process of how do you take noisy observations and use them to draw conclusions or infer what's the actual reality out there. And so the inference is what we're doing all the time when we are sort of judging the world. Learning is there's a bit of a fuzzy boundary, but you can think of learning as the thing we do to update the process that we use to form inference, right? And so, if inference is relying partly on our observations and relying partly on what we our memories of what we observed in the past, then learning might involve something like changing the relative balance of how much we rely on the observations versus our memories.
Yeah, it's very interesting. So, actually, now that you mentioned that, so I'm a competitive speed cuber. So I like make a lot of decisions when I'm doing a solve, for instance, in a competition. And what you just said about learning and kind of, using that to inform your future decisions. For example, if I do a certain sequence of moves and I do it, hundreds of times over lots of solves, and I find that my fingers tend to like turn very smoothly for it, I tend to do it more, and I guess maybe that's like leaning into muscle memory a little bit too, but I'm curious, like what kind of from your perspective and your research and decision making, what do you see when you look at someone like me? solving a Rubik's Cube and, refining my approach over hundreds of solves? Like, what kind of principles do you see at action there?
Yeah. Well, first of all, I look at and I'm super impressed. And I
Oh,
just, in that little demonstration that you showed there, you've already proven that the dexterity of your fingers and your mind is
yeah.
well beyond what I could ever do with a
Thank
Rubik's
you.
Cube. It's awesome. Um, yeah. So that's a great example of kind of the three basic components that we think of in these sort of very simple kinds of tasks that we use. The first part is what do you see, right? And the Rubik's Cube is a nice example that the colors are the information carrying visual cues that you're using in order to solve it, right? So the first thing that your brain has to do is to decide what it is that you're seeing. And in this case, the colors are designed to be different enough that it's not really a difficult decision. But
Yeah.
you can imagine, and I'm sure these exist, Rubik's cubes where the perceptual part of it is hard too, where they purposely
Yeah.
make it so that the different
Those
colors
are a
look
thing.
very
Yeah.
much like each other.
Yeah.
Okay, so there are such cubes.
Especially in the dark, actually. So what happens in the dark is you'll see the opposing colors like white and yellow, orange and red. They tend to if I think the cube is solved in the dark, they'll actually be mixed up because I can't differentiate between those colors because it's just so dark. So
Yeah,
that is
right.
something that happens. Yeah.
Yeah, so that's a problem your brain has to solve, right? So,
Right. Yeah.
so the color information is coming through your retina. It's coursing its way through the brain into visual cortex. It's dividing the information into different streams, and the lines that constitute the edges of each of the cubes, that is going to go down one part of this pathway. The color information is going to go down an overlapping pathway, but maybe slightly different neurons.
Yeah.
Um, and your brain is making decisions about what it is that it's seeing there.
Yeah.
Once that information sort of gets through the visual system, then there's this whole other set of processing that you have to do and make a decision about what do you want to do, right?
Right.
What is the strategy that you want to do in order to take advantage of the degrees of freedom of the movement of the cube that will align the colors in the way you want to. And so that's where it now starts I can only wave my hands around and sort of make up things about where in the brain that happens because that's a sort of abstract reasoning thing that we have less of a handle on.
Yeah.
But then once you do that, then there's the actual motor control, right? So once you've decided this is my plan, you have to activate it. And just like you were talking about, it involves, what you call muscle memory, but it's more than just muscle, right? It's your memory isn't in your muscles, it's in the neural circuits
Yeah.
that
Yeah.
control the muscles. And that's part of a decision process too. How is it that what is the decision that your brain is making in order to sort of convert this sort of abstractized plan about how you want the cube to end up to actual movements of your fingers that will cause that to happen. So there's this sort of cascade of things that are going on that we try to gain insights into by controlling experiments.
Yeah, it's very fascinating. So I actually had a question pop into my ma mind as you were explaining that, and I'm not sure if this makes sense, but one of the things I'm wondering is when I'm like solving a cube, or just in general for any task, like any, for example, like playing a sport or something, how much of like what's happening in that moment, like my actions are necessarily conscious, like me, or not conscious, but like me actively thinking about them and choosing, or is it more of like an unconscious reflex? Just based on what I've done hundreds of times before. For example, like if I'm doing an algorithm, I'm not thinking about those moves, but am I still technically making a decision to turn my fingers the way I am? Yeah, I guess you can talk
Yeah.
about that. Yeah.
Yeah, no, it's another great question. And now it starts to get into a bit semantic arguments about is a
Okay.
decision only a decision if you're consciously aware of it, or
Right.
is there something about what your brain is doing when it is maybe more sub or unconsciously still making judgments, but you're not controlling it?
Hmm.
That question aside, I totally agree with you that what you end up doing, particularly as you gain more experience with something, is that there are parts of it that become more automatic than others, and
Yeah.
that's a very active line of study, and it appears as though that when you're consolidating your knowledge, and particularly in the context of sort of motor control, that you're invoking different circuits than you do when you're first exploring those motor
Right.
outputs in order to solve a task, and that there's something kind of magical about how the
Yeah.
brain is able to do that in what feels like a very seamless way as you're learning, as you're learning and you're getting better and getting to the point where you are, where you can do all this very quickly. It's
Yeah.
not like in that process you've had any real conscious awareness of this transfer in your brain of
Right.
where the processing is happening. It's just sort of it's going on. And the really neat thing I think that differentiates us in one of many ways from artificial systems, right, is that as your brain changes how it's processing these things, there isn't a point in that process where you have this catastrophic loss of ability to do these things, right? That somehow it's able to maintain the learning while also maintaining the ability. And there's something that's really neat about that balance that doesn't seem to be as easy to capture in artificial systems where they have to explicitly separate the performance mode from the learning mode, because if they start to try to do them together, then weird things happen.
Yeah. And well, one last thing about the Rubik's cubes, I think
Yeah,
sometimes like in my some of my like fastest solves, I like look at myself like after solving, I'm like, wow, like I didn't even think too much, but like I'm just surprised that my fingers are able to move that fast. Or sometimes I'm like doing an algorithm and I have this like brief like outside like the cube moment where I'm like, how am I even turning this fast? And I think
right.
it's interesting to think about how like our brains are almost like more powerful than we can like, understand because, whether it's muscle memory or many of like any of the other processes that I can do almost in like a subconscious way. It's always really, really interesting.
Yeah.
Um, yeah, so one of the things I saw that or one of the parameters I saw that you guys study at your lab is a speed accuracy trade-off. So I'm curious if you could elaborate on what that is and how you studied it.
Yeah, so a lot of what we do feels instantaneous, right? So when you look out in the world, it feels like we're seeing things immediately.
Yeah.
It turns out that that's not true. That our ability to perceive the world and to do lots of things actually takes a finite amount of time. And in fact, just to give a pitch for my university here,
Uh,
one of the first places that studied quantitatively the amount of time it takes to make perceptual judgments is Penn. The Penn Psychology Department was founded by one of the people that was sort of early in those studies.
oh wow.
And there's a really interesting history, and there's histories of science that make arguments that I think are very compelling. That studies of time and reaction time that came about from all of the usefulness of time in navigation, for example, right in the naval-based empires of many centuries ago, that was the birth of experimental science. That people cared so much about very precise time judgments, that measuring our ability to measuring the timing with which we make judgments was the first sort of really well-controlled experimental sciences that became the foundation of a lot of modern science.
Wow.
So there's a real kind of rich history of all of that. And so from those studies, it was clear that almost any perceptual judgment that we make, that it turns out that the longer time you give someone to observe a stimulus, whether it's a visual stimulus, an auditory stimulus, or else, there's some range of time over which your ability to perceive it gets better. And this can be as short as tens of milliseconds, it can be as long as hundreds of milliseconds, but it's measurable. And the basic idea behind it is, and the models behind it that are now used in decision-making models and everything else, at their core are really simple, which is that if the information you're getting is sort of incomplete or noisy, then a natural thing to do is to try to signal average. And the degree of freedom that in principle we always have to signal average is to take more time. So that it might not be that the signal is spread out over space, but in general, the world is stable enough that if you wait a little extra longer, you'll get a little bit more information
Right.
and you can signal average. Well, that's at the core. So once you are signal averaging over time, then there is an inherent speed accuracy trade-off. The
Oh
shorter
yeah.
time you take, the less averaging you're doing, and the less able you are to extract the signal from noise. The longer you take, the more you're averaging, the better you can do. And so inherently, taking more time gives you higher accuracy. And so they call it a trade-off because in
I see.
general, you
Okay.
assume that you'd like to do it as quickly as possible. So it's better to do it fast. So there's going to be incentives to get things done quickly, but if you try to get things done quickly, then you have to sacrifice accuracy. So there's some balance in between that our brains try to maintain.
Yeah. That's interesting. And actually this sparked another question in my head. So I remember one time I read that Einstein like he would have like the same clothes like planned out every single day so he wouldn't have to like think about his clothes and save his like brain power for
Yeah.
his science experiments. And I was curious like is decision fatigue a thing where like if you're just making a lot of decisions a day or like I guess this might depend on the kind of decisions too. Does that like kind of almost reduce your kind of energy or output?
Yeah, it's a great question. It's almost as if you've read the mind of people in my life. That's a very active area of research that we're doing
Okay.
now.
Okay. Yeah.
And I think that there are all sorts of trade-offs in decision making. Speed accuracy is one. The one that's relevant to what you're talking about that we talk about is like an accuracy effort trade-off. And it may be
Okay.
well related to speed accuracy as well, that the longer time you take also implies that you're using up more computational resources in order
Right.
to solve the problem. And it may be that you're not willing to do that. And it may be that time is one resource, but it may be that there are other resources that we care about also. And I
Yeah.
think that it's one of our hypotheses that builds on a really rich set of ideas that's been around for a while now called bounded rationality that says that everything our brains do uses resources, uses cognitive resources, uses time, uses energy, metabolic energy in the brain. And so, in general, when you think about our ability to make decisions and do other things, you can't just say, "Well, well are you doing?" Full stop. You have to ask questions of the form, how well are you doing relative to the amount of resources that you're willing and able to apply to the problem?
Yeah.
And we're not really going to understand how well people do until we understand what are the resources that they are using in order to solve the problem.
That makes sense actually. Yeah. I'm glad I asked that because that kind of just came into my head, and it's something I've kind of wondered about too. But now is the perfect time to ask someone
Yeah,
about
that's a
it.
great question.
So another question is kind of what you mentioned like really, really early in the interview that like we have different almost like perceived weights of decisions. For example, like deciding where you're going to school compared to what clothes you're going to wear, like we just talked about. So when we're making like these big decisions, let's say you have a choice A and choice B, and these are like really, really big choices. For example, not just like choosing where to go to school, but like for example, choosing a house to buy. And there's various pros and cons to A and B, and either one of these decisions could like potentially shape the trajectory of your life. So what's kind of going on in our brains as we make these decisions? Like
Yeah.
these big like X or Y, A or B kind of.
Yeah, I wish I knew the answer to that question.
Yeah.
Particularly as the father of three teenage and now post-teenage children, knowing what's going on in everyone's head when they're making decisions, it
Yeah.
would be good to know.
Yeah.
But I mean, my general feeling is that the bigger the decision, the more complicated and idiosyncratic the process, and the less able, certainly I am, to extrapolate easily what we learn from these
Okay.
simple cases to the more complicated ones.
I see.
I think in general in some cases there's um, time then matters a lot. Like the bigger decision, the more time people takes.
Mhm.
And now you're moving beyond the speed accuracy trade-off, which, as I said, operates in this pretty restricted regime where you can make very sort of quantitative claims about the amount of information you're getting. And then once you get past that short amount of time and you take more and more time, well, it's not about like that's the only way to reduce signal and noise. It's more like now you're considering all sorts of possibilities that maybe start to tie you up in knots and bring you around in circles, and that it just gets harder and harder to
Yeah.
actually quantify and measure.
It's something really fascinating you just said that caught my attention. You said it was as these decisions become like bigger and bigger, the process almost like you see it as becoming more idiosyncratic. And
Yeah.
actually, this just brought to my mind something. Some of my friends that I've met over, the years, I've noticed like compared to me, so whenever I have a big decision, I'm very and everyone's different obviously, but for me personally, I like to be as logical as possible. Try to map it out like almost quantitatively, like what are the pros, cons, like try to get like a very logical understanding. But some people I've met almost they'll like literally flip coins or like they'll look at the time and like make a almost choice based off some arbitrary value that's
Yeah.
completely outside of their control. So I'm curious like How does that kind of, show up in your research, maybe like how people, like make decisions either based on logic or literally like flipping a coin, for instance?
Yeah, yeah. One of the really fundamental questions that we want to ask doesn't answer your question directly, but I think it's an important first
Okay.
step in that direction. So even before you could ask, how is it that people weigh these different factors, right? Why is someone weighing the sort of logical data that they've collected versus the maybe their distaste for spending a lot of time on it, or whatever it is that's motivating them to flip a coin. Even more basic than that, like how is it the brain even combines information from such different places, right? Like, the example that we give a lot is like in a restaurant, that you might base your decision on the smells that are coming from the kitchen, and you might base your decision partly on the prices you see on the menu.
Yeah.
But like, how do you even combine that information,
Yeah.
right? What are the units that your brain uses that says, well, this much smell versus this much price increase is how I want to balance it, right? And so those are the kinds of questions that we're interested in. So is there kind of a principled way we can think about the brain sort of expressing all of this information, maybe in some kind of common currency or common framework that
Yeah.
that ultimately, like, there's idiosyncrasies to how you choose the values you're assigning them to them, but at least you're using a cohesive system that allows you to do that in the first place.
Yeah. Yeah, I just think that that's actually interesting just because I know I always used to wonder like how are you like making your decision off those factors, but when I think about myself as you were explaining that, I've thought about a lot of choices I've made that were simply like just completely random. For example, like maybe a number that like meant a lot to me that day just because of something that happened earlier, or maybe like at Panda Express they give you like your fortune cookie, like the paper, and then that actually might influence my choices the next day. So it's always interesting to think about what factors go into making decisions.
Yeah, right.
Um, One of the things I wanted to ask you about is, you do a lot of computational modeling in your
Mhm.
work. So I'm curious, like, what kind of, I guess, like numbers or data are you doing like computational modeling for when it comes to decision making and studying that process?
Yeah, so there's lots of different kinds of models and lots of different sort of rationales for them that have lots of different uses. And so an example of the kind of models that people do that's not of the sort that we do is you could build a model based on what you think of as sort of basic brain connectivity, right? You could start with the brain and say, all right, if you had a bunch of neurons that look like this, then what would they do? Like, how could you wire them up in order to solve a decision problem? And that, in a super hand wavy way, that's how artificial neural networks started, right? Like
Yeah.
let's think of sort of an abstract version of connectivity. We come at it from another direction just because it's just sort of what we do, and I think it's interesting, and think much more abstractly about from a sort of statistical perspective, if you're given this information, how would a statistical engine sort of optimize its ability to extract signal from noise from this information in order to make a decision? And so we tend to think about probability codes. So when we've been talking a whole bunch about noise and uncertainty and signal and noise, another way to think about it is that things in the world from our perspective are probabilistic. When I look out, on a foggy day, I see something, oh, well, that car might be moving towards me, that car might be moving away from me. I need to kind of judge, sort of, I don't have absolute certainty on it. And so I have to somehow weigh in my mind what we would call a belief about that. And so if you think of a belief as a probability distribution where you're assigning, at least, maybe explicitly, maybe in some more implicit way that we don't understand, assigning probabilities to all of the alternatives, then we build models that basically are manipulating probabilistic representations where the interesting thing is you've got this probabilistic representation, but a decision is a choice where you need to put your money where your mouth is
Right.
and actually say, okay, well, I may be uncertain, but I'm either gonna step out on that curb or not, or off that curb or not. And so how is it that our brain converts this probabilistic representation into an actual choice?
That's yeah, that's interesting. Kind of continuing on this idea of, like you building models. One of the variables I saw that you guys use in your studies is pupil diameter. So I'm curious, like, how is like, I was just shocked. Like, I mean, from my like knowledge of neuroscience, like pupil diameter is, like reflecting maybe like an emotional state. But I'm curious, like, kind of how it's implicated in your research.
Yeah, I find I was just telling someone this story earlier that it was a grad student in my lab named Matt Nasser, who is amazing, and he now has his own lab up at Brown University.
Oh wow.
It was his PhD dissertation that started the work in my lab on pupil diameter.
Oh,
And there are lots of bases for it, but maybe the easiest one to describe is that yeah, people have known for a while, for almost 100 years, that modulations of pupil diameter involve emotions. They also have known for a while that it involves surprise. And so if you are startled by something, there'll be a change in your pupil size. And so the way people have tended to think about that traditionally is surprise in sort of the very much sort of fight or flight, like, this is a seriously surprising thing and I may need to run for my life. What Matt asked was, well, maybe there's a much more subtle version of surprise, and that a big part of how we process information in the world, and particularly a world that can be changing all the time, and tying back to this idea of we're constantly using sensory information and memory information to make sense of the world. Well, a really useful thing to know would be, has the world changed enough that I should abandon the memory information that I've been relying on and now start relying on the new sensory information because something changed?
okay.
And so that's a form of surprise, right? Did something
Yeah.
happen that surprises me relative to what I thought I had remembered or known? And it turns out that that subtle form of surprise is the kind of thing that we see in pupil size.
Fascinating. That's actually really interesting. Um, Okay, so my last question for you is, um, like in your research right now, what is one question that's kind of unanswered or it's been like really elusive that you're excited to tackle for the next couple of years and you're hoping to kind of make progress to?
Yeah. So, I mean, it's really, so the things that I've been talking about, this how does your brain sort of process all this information in a dynamic world? And what we're really interested in, what's the mechanism of that? And again, we're not the only people asking this, but we're very interested in this idea that, so basic neuroscience, you've got cortex that does a lot of interesting things. There's subcortical structures that do a lot of interesting things, but the things that they do is not static. And so in order to be flexible, what has to happen is that how your brain is processing information has to change depending on the circumstance, just like the surprise thing, right? Like
Yeah. Yeah.
when you are going from a mode where you are relying on memory versus relying on sensory information, something in your brain has to do that, right? And has to change the way that you're processing information. If you're relying on memory, then you're not putting as much cognitive resources into taking in the sensory input. But then as soon as you're surprised and you see that your memory is maybe no longer relevant, then all of a sudden you've got to process that information. And so how is that happening? And we think that one of the main control knobs are neuromodulators, these chemicals that get sort of dumped all over cortex that do something magical to sort of change how an existing network of neurons processes information differently under some new circumstance. And so we really want to understand that mechanism.
Yeah, it's really cool. And one last thing I'll add here is
Yeah.
right now it's actually tennis season. So what happened we got new courts this year for my school and we don't have like the wind screens on our courts. So what's happening is there's a lot of wind. Like really huge gusts of wind when we're playing. And last year that was not an issue. But this year when we started playing like just like about a month ago, as we're hitting the ball, it's a lot different with the wind. So all of our like kind of muscle memory with like hitting the ball, it has to change because on each side there's either wind blowing with the ball or against the ball, and that like truly does affect like how the ball, especially when we're hitting so close to the lines, like trying to get the opponent like hit the ball as far away from them as possible. The wind is almost like forcing us to kind of adapt and use that information in it. So as we're hitting our stroke, we have to think about, hey, should I put a little more spin on this ball so that it doesn't go as far out? And I just wanted to ask, is that like an example of this kind of having to modify how we're
Yeah,
making decisions.
absolutely. That's a great example.
Yeah.
Yeah, that's a really great example. Yep.
Yeah. So, on that note, Dr. Gold, thank you so much for joining me today. I'm really glad that we were able to speak because I had a lot of personal questions during this interview.
Yeah.
Yeah.
Look, thank you for having me. And if you permit me, let me just say just thank you and keep doing what you're doing. You know,
Oh,
science is at a difficult time right now, and more than ever, we need young people to be excited about science. And right, you're the future, not me, of the scientific enterprise. And to see you being this engaged and going out of your way to not only learn new things for yourself, but be part of a solution of actually helping other people learn about these things. I think it's absolutely wonderful, and please keep it up. And I look forward to hearing about great things that you're doing in the future.
thank you so much.